Drone swarms represent a fundamental shift in how air power is applied. Traditional air warfare relies on individual platforms controlled directly by human operators. Swarms replace this model with distributed autonomous systems that act as a collective. The unit is no longer the aircraft. The unit is the network. Early military drones were extensions of manned aircraft doctrine. They were remotely piloted surveillance or strike platforms. Control depended on constant data links and human decision loops. This limited speed, resilience, and scale. Swarms remove this dependency. Autonomous swarms operate through shared rules rather than direct control. Each drone processes local data and exchanges limited information with others. Behavior emerges from coordination rather than command. This allows hundreds of systems to operate simultaneously without overload. The primary advantage is saturation. Air defenses are designed to track and engage limited numbers of targets. Swarms overwhelm sensors and interceptors through volume and unpredictability. Even advanced systems struggle when engagement queues collapse. Cost asymmetry defines the threat. Individual swarm drones are inexpensive compared to missiles or fighter aircraft. Trading interceptors for drones favors the attacker. Attrition becomes acceptable. Loss is expected and absorbed. Decision speed increases dramatically. Autonomous systems react faster than human operators. Threat detection, target allocation, and maneuver occur in milliseconds. This compresses the battle space and reduces response time for defenders. Swarm intelligence enables adaptability. If one drone is destroyed, others reroute automatically. Gaps are filled without external input. The formation reshapes in real time. This resilience makes traditional kill chains ineffective. Mission roles are diversified within the swarm. Some drones act as census. Others carry weapons. Others serve as decoys or electronic attack platforms. The swarm functions as a combined arms system in the air. Communication is limited by design. Swarms do not rely on constant high-bandwidth links. They use short-range encrypted exchanges. This reduces vulnerability to jamming and detection. Silence becomes a feature rather than a weakness. Artificial intelligence underpins coordination. Machine learning models handle pattern recognition and threat prioritization. These systems are trained on vast data sets. They do not require perfect information to act effectively. Human involvement shifts to mission definition rather than execution. Operators set objectives and constraints. The swarm determines how to achieve them. Control becomes supervisory rather than tactical. Ethical and legal frameworks lag behind capability. Autonomous lethal action challenges existing rules of engagement. Attribution becomes complex. Responsibility is diffused across systems and algorithms. Strategic implications are profound. Swarms enable persistent presence without risk to pilots. They lower barriers to entry for air power. Smaller states gain capabilities once reserved for major powers. Countermeasures remain under development. Electronic warfare-directed energy and cyber effects offer partial solutions. No single defense addresses all swarm behaviors. Defense becomes layered and reactive. Integration with manned platforms accelerates impact. Crewed aircraft act as command nodes or launch platforms. Swarms extend reach and reduce exposure. The human-machine team replaces the lone pilot model. Drone swarm evolution is not incremental. It is structural change. Air superiority shifts from platform performance to network behavior. Control of the sky depends on algorithms, coordination, and adaptability. This transition is already underway. Future conflicts will not be decided by the fastest jet or the stealthiest airframe. They will be decided by which side controls the swarm.